Practice exam for Unit 4, question number 1. A pendulum is pulled to the side and released. What is its frequency if it passes through its rest position 0.15 seconds after it's released? So, we have a pendulum, it's pulled to the side and released. So it's going to go back and forth. Oops, oh, that was not a very straight line. Let's try that again. That's better. And it says, what is its frequency? So to find the frequency, we need the period because of this formula here. It takes 0.15 seconds to go from this point to its rest position. This is its rest position or its equilibrium position. So you have to ask yourself, if it takes 0.15 seconds to do that much of a swing, how much does it take to do, or how long does it take to do a full swing back and forth? And you can clearly see that 0.15 seconds represents a quarter of the period, a quarter of the swing. And so we're going to multiply, not by a quarter, we're going to multiply this by 4, and we're going to get 0.6. So it takes 0.6 seconds to do one complete cycle, which is there and back. And then it's pretty straightforward. You divide those numbers and you get A. Number 2 is a graphing question. The graph shows data taken during experiments to verify Hooke's law. What is the spring constant for the spring used in this experiment? Okay, so on the y-axis, we have force. And on the x-axis, we have position or displacement or the x value. And Hooke's law is and we want to find out what the spring constant is. So we rearrange that formula for K. We get F over X. We're just going to ignore the negative. The negative, just as a reminder, is to indicate the restoring force is always in the opposite direction of the displacement, but it's irrelevant in this question. So if you rearrange it, you get F over X, which you should immediately recognize as being the rise over the run. Therefore, the K value or the spring constant for this graph is simply the slope of the line. And we can go follow up our line. Hopefully, if we follow up the line, we can find some point where it intersects. Well, that one's pretty close. I think that looks like the closest one. Yeah, let's go with this point right here. And just find the rise over the run. So in this case, the rise is going to be 10 times 10 to the 2. And the run down here is going to be 6 times 10 to the negative 2. And then we punch that in a calculator. Now, since it doesn't go exactly to that point, we're probably not going to get the exact answer, but we're just going to pick the one that's closest. So 10e2 divided by 6e negative 2 equals 16,666. 0.6 repeating, which you can clearly see is if we round that off, we actually get A. So you're just going to pick the closest one. Okie dokie. Number 3, a block on a spring. So we have a horizontal spring oscillating back and forth between points 1 and 3, and point 2 represents its equilibrium position. And the question says, which points, 1, 2, or 3, best indicate where the acceleration of the block will have the greatest magnitude? So let's just review. This block is going to oscillate back and forth between position 1 and 3. Therefore, let's talk about the velocity and acceleration at all these points, 1, 2, and 3. if it's oscillating back and forth between 1 and 3, the velocity at this point must be 0. So for a fraction of a second, it's going to be 0 because it has to change direction. And likewise, the velocity over here must be 0. Therefore, you must have a maximum velocity in between those two, which would be at the equilibrium point. So the velocities are 0 on the extremes, and the maximum is in the middle. The acceleration is just the opposite. At this point is where you can have your maximum acceleration, even though you're going to say, well, it's not moving. Well, for a fraction of a second, it's 0. But then the acceleration is the maximum because you've stretched that spring and it's got all this elastic potential energy, and therefore it's going to accelerate the most here. And then when it gets to here, the acceleration will actually be 0. And then again, you'll get another maximum acceleration on the other end. So the answer to that question is 1 and 3, A. Moving on, number 4, a pendulum. A 3.92 kilogram pendulum bob is attached to a 4.5 meter long string. The pendulum is pulled sideways until the string makes an angle of 18 degrees with a vertical. What is the restoring force? Classic pendulum question. This is the restoring force. So you pull the pendulum back. This is your 18.5 degrees. We want to know what the restoring force is. The only other, we're given two other pieces of information. One is the length of the string, and the other is the mass of the pendulum bob. And that's the one we need, because in this right angle triangle, we have the opposite side. We either need the adjacent or the hypotenuse here. Now, we have the length of the adjacent, but we don't have a force associated with this. So you can't put 4.5 in there and then solve it, because that's a length, and this is a force measured in newtons. So don't fall into that trap. Given that you have the mass, though, you can automatically calculate the force of gravity. So now we have a force over here, and we have a force over here. This is the hypotenuse. So we're going to use sine of 18.5 equals the opposite, which is the restoring force, divided by the hypotenuse, which is the gravitation. And you can put the negative in there if you want. Again, it's kind of irrelevant to the question since the direction is obvious. The restoring force is back to the direction of the restoring force is back to the equilibrium position. But that's how you do that. The restoring force equals sine of 18.5 times the mass times gravity, and you end up getting an answer of 12.2 newtons, which is B. Moving on, we have a similar question. We have a 120-gram arrow is shot with a bow that has spring constants of 4.7 times 10 to the 2 newtons per meter. If the archer draws the bowstring back a distance of 66 centimeters, what is the initial acceleration? Okay, this is one where there's a lot of information, so it's a good idea to write down what we have. We have the mass, 0.12 kilograms. We have the spring constant, (470 newtons per meter, or 4.7 times 10 to the negative to the positive 2. And we have the x value, 66 centimeters, 0.66 meters. And we want to know what's the acceleration. Well, there are two ways you can do this. One, you can use the k and the x to solve for F, the force, and then you can just use F equals ma to solve for the acceleration. So that way will work fine. Or you can equate the two forces. You can say that the net force here equals the restoring force. Therefore, ma equals negative kx, and we're going to solve for A. And that's it. That way you can do it in one step. It doesn't make any difference which method you use. The first or the second, you're going to get the same answer. Either way, once you plug those numbers in, you've got everything there. It turns out you get an answer of 2.59 times 10 to the 3 meters per second squared. Number 6. A mass is at rest on a horizontal frictionless surface is attached to a spring which is compressed the distance of 7.5 centimeters from its resting position. If the mass accelerates at 29.9 when it is released, what is the spring constant? Okay, this question is very similar to the previous question, except for they're solving for a different variable. Right? You have the mass. You have the x value, the displacement, and this time they give you the acceleration. And they're asking you to solve for k. So without going into all the details, it's just going to be the same thing. Ma equals kx. Plug in the numbers, get your answer. That answer turns out to be B. 2.07 times 10 to the 3. All right, number 7, we've got wave phase points. So here's a wave. And the first question asks, so actually there's only one question because 8 is eliminated or omitted. Listed below are 4 pairs of points on the wave train. For which of these pairs is the distance equal to 1 wavelength? So let's just review. The obvious 1 wavelength is here. 1 crest, 1 trough, that's a wavelength. So now we have to determine, though, if I go from C to G, is that a wavelength? C to G. Not even close. Erase that one. How about A to J? Well, you probably can see that one. Oh, wait a minute. Actually, A is right here. A. So basically what you want to do is you want to end up in the same place that you started and making sure that you completed 1 full wavelength. So A to J. Oh, okay, yep, that's a full wavelength, right? Because we started here and we end up at the same place and we have a crest and we have a trough in between those. So A to J, you are a winner. What else? B to K. Run out of colors. B, let's go green. B to, so we're starting at this crest here, at the top of the crest. So that means to make a full wavelength, we must get back to the top of a crest. Yep, check mark by that one. That is also 1 full wavelength. What about D through M? D through M. D, M. Yeah, that's clearly a wavelength. So 2, 3, 4, the answer is B. Number 9. Okay, now these ones, this is where they start to get to be a little more thoughtful about these ones, and you have to think a little more. A spring is stretched to a length of 6.12 meters along the floor. So you got a spring, stretched it out. This length here is 6.12 meters. A 1.86 meter long pulse takes 0.268 seconds to completely reflect from the fixed end of the spring. Now, what that means is it's not that the pulse takes 1.6 seconds to go like that. Oops, I wanted that blank. There and back. No, that's not it at all. When it says when it says it takes 0.26 seconds to completely reflect, what it means is once the pulse, so here's the pulse, here's your pulse, and it travels this way, and then it hits here, and it's a fixed end of the string, so what's it going to do? It's going to invert when it comes back. So it'll be inverted when it comes back. This value here is the amount of time it took to do that, to invert, okay, or to be reflected. So not the amount of time it takes to travel across the spring, but the amount of time it takes to reflect. Okay, so we can consider that. What we need for this, the question is asking, how long does it take the pulse to travel from your hand to the fixed end of the spring? So the question is asking this, how long does it take to do that? Right, and we have, for lots of these questions, you can use the formulas interchangeably. Velocity equals distance over time. And I'm going to use that one because it makes the most sense to me. I want to find out how much time did it take to go this distance here, there, and then back. Now that distance there, and back is not 6.12, it's double that. So it's 12.24. So T equals D over V. And I've already got that. What I need to do is calculate my velocity. And how am I going to calculate my velocity? Well, I can use the same formula if I want. I mean, you can use the universal wave equation, but the universal wave equation is this formula here. So I could just use V equals D over T. And in this case, this is my D, right? Because that's the length of the pulse, and it takes that many seconds to reflect. So this would be my T. Okay. And if you divide those, you're going to get 6.94. And that's the velocity of the wave, which I can then put in right over here, and that will give me a time of 1.76 seconds. All right, so you may want to watch that example again, just so you understand what these numbers mean. I mean, you could do it also like this. You could say that the velocity equals the wavelength times the frequency, and the wavelength is 1.86, and the frequency is 1 divided by the period, 1 divided by the period. And you see how you end up getting the same thing as you did over there. So whatever way works for you in your head, use that method there. Personally, I just like the V equals D over T, because as long as I understand that this is the wavelength or the distance, and I understand that this is the period or just the time, then I'm gold. Okay, oh, that's a long video. We'll stop here and go on to part 2.